Lesson 6.3, Medians and Altitudes of Triangles. A median of a triangle is a segment that connects a vertex to the midpoint on the other side of a triangle. So that's a median because it goes from the vertex to the midpoint of the other side. There's another median, goes from the vertex to the midpoint of the other side. And that's another median. It goes from the midpoint to the vertex on the other side. Notice they all meet in one point. What's the name of the word? It says that we describe lines where they meet in one point. That's right, concurrent. Those little point to the concurrency is called the centroid. The centroid is the balance point. So if you were to cut this triangle out of like cardboard, it would balance on the centroid. The medians of a triangle intersect at a point that is 2/3 of the distance from each vertex to the midpoints of the other side. So on this median, that distance is 2/3 and that is 1/3. So it divides our median into 2/3 and 1/3. The 2/3 is between the centroid and the vertex. The 1/3 is between the centroid and the side. Let's try an example. In this picture, each path goes from the midpoint of one edge to the opposite corner. The paths all meet in P. So, in other words, these are medians. Those are congruent. Those are congruent. And these are congruent. So, if FSC is 100, find PS and PC. Well, if it's the centroid, so medians, then this is 2/3 and this is 1/3. So PS is 1/3 of SC, or 1/3 of 2100 feet, which is 700 feet. PC is 2/3 of SC, or 2/3 of 2100 feet, which is 1400 feet. If BT is 1,000, find TC and BC. Alright, since T is a midpoint, TC is going to be the same length, or 1,000 feet. And BC is just the two added together, so it's 1,000 plus 1,000, or 2,000 feet. Alright, if PT is 800, PT is 800, find PA and TA. Alright, now this one's... Alright, so PT is the shorter part. It's the part between the centroid and the side, so that's the 1/3. So PT is 1/3 the whole length, which is TA. PT, though, is 800. So to solve for TA, we need to multiply by 3. So TA is 2,400 feet. PA is 2/3 of that, or if you like, PT is the 1/3 and PA is the 2/3. So if I just double it, I should get PA. Let's see what I mean. So PA is 2/3 of TA. and TA was 2,400. So you multiply those and you get 1,600 feet. But notice if I take that 800 and multiply it by 2, I get 1,600 feet. So if you just take the shorter one, which is the 1/3, and double it, you get the other part, the 2/3 part. Would you pause this and try numbers 2 and 6? Alright, let's try another example. Find the coordinates of the centroid of the triangle ABC with those vertices. So maybe we should start by graphing them. So we have 0, 4 is point A, -4, -2 is point B, and 7, 1 is point C. Alright, so let's see. To find the centroid, we're going to need to find some midpoints. So, let's find the midpoint of AB. Remember, the midpoint formula is x1 plus x2 over 2, y1 plus y2 over 2. So for AB, be 0 plus -4, those are the x values, over 2. And 4 plus -2 over 2, those are the y values. Which gives me -4 over 2 and 2 over 2. So -2, 1. So that's the midpoint. So there's that. Now, the centroid splits that into 2/3 and 1/3. So we could come up with the length. 1, 2, 3, 4, 5, 6, 7, 8, 9. So our length is 9. So let's just go with 1/3 of 9 is 3. So 3 spaces over, 1, 2, 3. That should be my centroid right there. Just to verify that, let's go ahead and find another median. So the midpoint of, let's go with AC, be 0 plus 7 over 2, and 4 plus 1 over 2, which gives me 3.5 and 2.5. Which is right there. Notice that line goes right through our centroid. And let's just do the last one just for kicks. The midpoint of BC is -4 plus 7 over 2. And -2 plus 1 over 2. So -4 plus 7 is 3, divided by 2 is 1.5. -2 plus 1 is -1 over 2 is -0.5. So 1.5, -0.5 is right there. Draw our median. Notice that is our centroid. That centroid right there appears to be at 1, 1. So did you have to do the others? No, but it verified it and made it look good. Why don't you pause this and try number 16. An altitude of a triangle is a segment from a vertex but perpendicular to the opposite side. So a median went from vertex to the midpoint. Altitudes are vertex perpendicular to the side. We typically call them the heights. So if I were to draw an altitude there, notice it would be the height of the triangle. It's another altitude and another altitude. Notice the altitudes all meet in a single point, so that means they are concurrent, and it's called the orthocenter. The prefix ortho means perpendicular. The lines containing the altitudes of a triangle are concurrent. That just means that, well, they're concurrent, but it's not really a special point. However, in an acute triangle, the orthocenter is inside the triangle, as you see there. On a right triangle, the orthocenter is on the right triangle. So, if that's perpendicular, then it turns out that that side is one altitude, that side's another altitude, and that would be the other altitude. So the point of concurrency is right there on the right angle. And for an obtuse triangle, the orthocenter is outside of the triangle. Because you'd have to extend a side to draw the perpendicular. So we'd extend those. You see they all meet there-ish. So let's find the orthocenter of this triangle. Ooh, what type of triangle is it? Since two sides are congruent, that makes it isosceles, and it looks like it is obtuse isosceles. Alright, so we need our first altitude, which is actually looks like it's drawn for us. This looks pretty perpendicular. How am I going to draw the next one? Well, what we're going to do is we're going to extend the side. And then we're going to draw a segment perpendicular to that side, to that extension. Okay, we'll do the same thing to the other side. We're going to extend it. And then we're going to draw an altitude perpendicular to it. Something like that. And then if we extend our other altitude, it's right there. So the orthocenter there is there. It's an obtuse triangle, so the orthocenter is outside the triangle. Why don't you pause this and try number 18. In an isosceles triangle, the perpendicular bisector, the angle bisector, the median, and the altitude from the vertex angle are all the same segment. So here's an isosceles triangle. And that's from the vertex angle. So if it's the perpendicular bisector, so you can see it's perpendicular and the parts are congruent there. But the two smaller triangles that are made are congruent by HL, or if you'd like SSS or whatever. By CPC-TC, those angles at the vertex angle would be congruent, so it's also an angle bisector. It goes from the vertex to the midpoint of the other sides, that makes it a median. And it goes from the vertex angle perpendicular to the other sides, that makes it an altitude. Alright, let's do a proof. Given we have an isosceles triangle with a median, prove it's an angle bisector. Okay. Well, Start off with our givens. So triangle ABC is isosceles, and BD is a median. Guess this is still statement 1. All right, statement 2. Let's go with our first vocabulary word, isosceles. That means two sides are congruent. In this case, AB is congruent to BC. And how did we know that? We used the word isosceles. So that's the definition of isosceles. So what can we do next? That's right, we can do the same thing with our vocabulary word median. Median goes from the vertex to the midpoint of the other side. If it's the midpoint, then we know AD is congruent to DC. And how did we know that? Because we used the word median. All right, so what do we have? I see two little triangles in our picture. Maybe we could say that they're congruent somehow. We have two pieces that are already marked. Is there another thing that we know is congruent between the two triangles? That's right, they share side BD. So since they share it, we can say BD is congruent to BD. And if we say it's exactly the same thing, that is reflexive. So now, why are the triangles congruent? Triangle A, B, D, congruent to triangle, corresponds to A is C, B, D. And why? Well, we have the sides, so it's side, side, side. So now if those triangles are congruent, how can we get to the angle bisector part? Well, that's right. We could say those two angles are congruent. So angle ABD is congruent to angle CBD by, well, the triangles are already congruent, so the parts are congruent by CPC/TC. Corresponding parts are congruent, triangles are congruent. Well, now our segment splits the angle into two congruent angles. Therefore, step 7, we can say BD is an angle bisector. Definition of angle bisector, which simply says it splits the angle into two congruent parts. And there we have our proof.